I just wanted to go back over one point of the proof last time of Morley's theorem, because I think it deserves a more. So this theorem said that if minus kx is ample, then x is unirule. Okay. So remember, we proved it in positive characteristic. Okay, so I'm not going to redo the proof, but and then to pass from positive characteristic to characteristic 0. So assume for simplicity that x was defined over z. Okay, and we look at the scheme of morphisms from P1 to x, which in this case is also defined over z. So it's morphism over spec z. Okay, and so the proof in characteristic 0 tells you that the image of this morphism contains infinitely many primes. Okay, this comes from the reduction to characteristic P. So the point is that we want to know that the image contains the generic point. Okay? And this is not enough in general, and the problem might come from the fact that this space might have countably many different connected components. For example, so here you have spec Z. Okay, so 2, 3, 5, P. Okay. So over each point you might have one connected component of this guy. Okay. And doesn't tell you the image then will not contain the generic point. Okay. So what we need to do here is to take a piece of this space here which has infinitely many irreducible components. We need to take a quasi-projective piece. Okay. And this piece is given, so we need to replace this by a quasi-projective let's say subscheme. Okay. And one way to do that is to bound the degree. Okay, so we do that by bounding the degree of the curves with respect to some ample divisor. Okay. So in that case, so let's say here we have an ample divisor which is given. It's minus kx. Okay. So this you get by using the second. This you get by using the second Banach break. Okay, which tells you that you can decrease the minus kx degree until you get to you get a bound like this, where n is the dimension of x. Okay, so the characteristic P case tells you that you can always find a rational curve through any point, but moreover with this bound. Okay. So we're using again here that minus kx is ample because the degree, you need to bound the degree with respect to some ample divisor. Okay. So this is just a point I wanted to make. Also there's a slight point which here we prove that there is a rational curve through any point. This is not exactly the definition of being uniole, but I'll let you think about this. Okay, there's another theorem which expand this one here, which is due to Miyaoka and Mori. So Miyaoka and Mori. So it says the following. So let me get the hypothesis right. X projective variety. again assume that there is a curve such that minus kxc, or let's say kxc is negative. Okay, I'm not assuming that x is Fano, so I'm not assuming that minus kx is ample, it's just negative, kx is negative on one curve. Okay, let me move. Okay, then, and I choose also an ample divisor. Okay. So in some sense, I choose a projective embedding of x, then there exists a rational curve on x through any point of the curve, through any point of C, or let's say, to be more precise, rho of C. Okay, so C is P1. No, C is not P1, sorry. There exists a rational curve on x through any point of rho of C of bounded h degree. There's, the statement on the notes is more precise, but so in other words, there's sort of a universal bound, something like this, which depends on x and h only, that bounds the degree of the rational curve. And so the proof goes along the same lines, and this bound here is necessary if you want to go again from positive characteristic to zero characteristic. Okay, so the last chapter of of my notes is the Kohn theorem. Mori version of it. So first of all, I need to switch my point of view a little bit. Earlier in the other lectures, I defined a series of cones in the Néron-Serre group of X. So X here is projective variety. Okay, so this is, I take with real coefficients, so this is a finitely dimensional vector, or real vector space. And so there were many cones here. I'll just, remember there was the pseudo-effective cone, which is the closed cone spanned by classes of effective divisors. And inside this, I defined the Neff cone. Now I want to look at the dual situation. So what is the dual situation? Well, remember that this guy here was, let's say, the set of equivalence, numerical equivalence classes of Cartier divisors. And numerical equivalence was defined by taking the intersection of Cartier divisors with curves. Okay, so the dual situation will be to look at. So then the notation is a little bit inconsistent. This is also usually written as N1X R. So upper one means codimension 1, and here lower one will mean dimension 1. So this will be the numerical equivalence classes so the analog of Cartier divisors here will be what we call one cycles of real one cycles on X. Okay, so one cycles are just formal linear combinations so here I take my curves embedded in X. Okay, so irreducible, but not necessarily smooth. Okay, and so the NCs here are just real numbers, and these sums are finite sums. Okay, And so what is the numerical equivalence class? Equivalence in here, well, it's given by the same thing, okay? We say that two cycles, I don't know, gamma and gamma prime are numerically equivalent if and only for all divisors d, we have d gamma equals d gamma prime. So it's a tautology to say that these two real vector spaces are dual one to another. Dual vector spaces. And duality is given by this intersection product. Okay? So this is duality of real vector spaces. There's also a notion of duality of cones. Okay? So here, let's say I'm talking about closed convex cones. And so if you have a convex cone in a real vector space, so convex cone in the sense that I've been using up to now, you can define its dual. So C dual will be the set. So C dual will be inside the dual of V, and it's a set of linear forms on V such that which are non-negative on all elements of C. Okay, so for all x in C, L of x is non-negative. Okay, so this is a very standard construction, and so you can prove, for example, that the dual of the dual is the same as the original cone and stuff like that. It's not completely trivial, but it's elementary. So if you think about it, the Neff cone was defined exactly in this fashion, okay? Because the divisor is Neff if and only if its product, its intersection product with any curve is non-negative. Okay, so by definition, this is the dual of, so the dual in the sense of duality of cones, is the dual cone to what we could call the effective cone inside n lower one of x. Okay, but it's usually called the Murray cone for obvious reasons. And I put a bar here because it's the dual cone. So this is the closed convex cone generated by classes of irreducible curves on X. Okay? So by definition, this is a duality. So here, there's also, it actually goes the other way. But we could also consider the dual cone to this one, but so it would sit in here. But I won't do that here. It's also an interesting cone. So the cone theorem has to do with the description of this cone here inside this finite dimensional vector space. So there's an important notion here about cones, is that of extremal ray. Okay, so what do we need to define here? Okay, so assume that we have a closed convex cone here. So closed, you understand, convex means that the sum of two elements is in the cone. We say that a ray, so a ray is something which looks like this. It's generated, positively generated by an element. So this is called a ray. It is extremal if whenever you have two elements in the cone, Z and Z prime, whose sum is in the ray, then both of them are in the ray. And the intuitive idea is exactly the one that you can have. So if you have a cone like this, if you have a, let's say you have a cone like this, so there's a round part and a so it's sort of an ice cream cone you've cut two pieces like this. Okay. So each ray. So here's the origin. So a ray is a half line passing through the origin containing the cone. So here they're all extremal. all the points in here span extremal rays. Okay, so this is an extremal ray. This is an extremal ray like this. This is also an extremal ray, but this is not. Okay, it's on the boundary, but it's not extremal because you can find two elements in the cone, let's say this one and this one, whose sum is in the ray, but they're not in the ray. Okay, so it's really, it's because there's sort of a flat piece here. Okay, so the extremal rays in here would be all the rays spanned by these boundary points here, plus the ray spanned by this. And so it's an elementary thing to prove that if C contains no lines, C is the convex hull of its extremal rays. Okay, so again, this has nothing to do with algebraic geometry, and it's not very difficult to prove. I forgot to say something in here.
So these cones are not completely polyhedral?
For example, no, I mean, here's one. I mean, at the moment, I'm talking about general cones, okay? Except in dimension 2. In dimension 2, you have no choice. I mean, you have no choice. So in dimension 2, a cone looks like this. So I was told it's not a slice of cheese, but it's a slice of pizza. But okay. But also, the whole plane is also a cone. Okay, and it has no extremal rays. Okay, so this is why you need this kind of hypothesis here. Even a half space is a cone, but it has no extremal rays. This is not extremal. Okay, because you can have an element in here. You can express it as a sum of an element in here and in there. Okay, and here it's not in the ray. So most yep.
Different from zero.
Yeah. Yeah, array is one-dimensional. Thank you.
So if cone is round, is every boundary ray extremal?
Yeah? I mean, it depends what you call round. I don't know. You could take that as a definition of a round cone. Okay, so let me go back here. It's also a general fact about cones that in this duality thing here, that the interior of the dual is the set of I can look at duality in both directions, okay? So the interior of the dual cone is also the set of linear forms which are strictly positive on non-zero elements of the cone. Okay? So in our situation, remember that the interior of the Neff cone is the ample cone. So in this way, we get a Kleinman's criterion. Which says that if you have an X projective scheme, a class Z is ample if and only if. Let me try to get the notation. No, so yeah, I suspected that this was not. Sorry. Let me go back to divisors. So a Cartier divisor D on X is ample if and only if for all Z in, so the dual cone, which is the Mori cone, except 0, dz is positive. Okay? So this is the difference between being positive on curves. I said this was not quite enough to be ample. You need to be positive on the closed cone generated by classes of curves. Okay? So if the cone of generated by classes of curves is closed already, then it's enough to be ample to be positive on each curve. Okay? But usually, I mean, in some cases, it is different. Okay, so we have this. So notice in particular that if X is projective, it has an ample divisor. So this ample divisor is positive on each point, non-zero point of the Mori cone. So in particular, it implies that the Mori cone contains no lines. Okay, if you take an ample class, let's say A, if you take, let me just put it in the plane, otherwise you won't see anything. Okay, so this is the orthogonal of an ample class. Okay, so this sits in N1 XR. And Kleiman's criterion tells you that the Mori cone is completely contained, apart from the origin, in one of the half spaces defined by this ample class. Okay. So I've done the drawing, the picture in 2 dimensions, but it's the same in all dimensions. Okay. You have any ample divisor, and it's a characterization of ample divisors, defines a hyperplane in this dual cone. And the Mori cone is entirely contained, the closed Mori cone is entirely contained in one of these open half spaces. So it cannot contain a line. Okay. So in particular, it is a convex hull of its extremal ways. So now I think I can state Mori. Are there any questions? You need to understand the setup. I mean, it's not supposed to be complicated. So Mori's theorem does not describe the whole cone, but it describes the part of the cone where the canonical class is negative. Okay? So remember, keep in mind that this space here is dual to the space of divisor classes. Okay, so each divisor on X defines a hyperplane in this space here. Okay, which is given by, so the equation here is just given by AZ equals 0. Okay, so let me state the theorem and then I'll explain. So X is a smooth, so this is very important. Okay, there exists a countable family of rational curves on X such that the minus kx degree, so the dimension is n, is at most n plus 1, and so this is the Mori cone. So there's a part where we cannot say anything. So I'll explain the notation in a moment. So this notation here means this is the part of the cone where the canonical class has a positive degree, non-negative degree. Okay. So remember, any divisor class, such as the canonical class, defines a hyperplane in. Okay, so This is the orthogonal of kx, okay? Same as I was considering here, the orthogonal of A, okay? So this is the part of the space where kx is 0, and then there's a part where it is non-negative, so it's behind this. And then there's a part where it is negative, okay? So it's in front of this hyperplane, okay? And this is the part that Maurice Theorem describes. Okay, so there exists such that, and moreover, the rays, these rays here, are all the extremal rays. So they are extremal, and they're all the extremal rays contained in the half space where kx is negative. Okay, so they are in that space here because kx gamma I is negative, and so these are all the extremal rays. So the picture that you can draw, which I think it's the cover of my book. It's actually not a very good picture, but I still draw it. So here we don't say anything about this part. Okay. But in that part here, it tells you that the cone looks like this. So you have extremal rays spanned by these gamma i's. There might be countably many of them. And also, I forgot to say that in the statement. I'll just say it orally. These rays are locally discrete in that half space. So it means that they can only accumulate on this hyperplane. Okay? So if there are infinitely many of them, they accumulate in here. So in that part, the cone is, look, it's not, but on the picture it looks like it's polyhedral. Okay? If you think about it, this is a picture that's okay in dimension 3. It is locally polyhedral, but in higher dimensions it's not true. Okay? So I don't want to spend time on this, but it's a mistake that's in a lot of papers and books written by eminent authors, that they say that it's locally polyhedral. It's not true. Okay. So let me do an example, and I'm sure you can guess which example it's going to be. So surprise, it's the blow-up of Pn at a point. So let me drop the field. H. So we already have the picture in the space of divisor classes. So we had standard notations, E, the exceptional divisor, and epsilon upper star of H. And here, epsilon upper star of H minus E. So this is an F cone, and this is the pseudo-effective cone, the whole thing. But I won't need it. So the F cone is just here. So this is a picture in N1. So let me call that X, N1X or NSX. R, two-dimensional. So now let's draw the picture in N1X. Okay, so I had the picture somewhere. Okay, there it is. So it's going to be two-dimensional, and it's not very hard to see that it's spanned by. Of course, there are many generators, but you can take, so one of them we already used. It was the class of a line contained in E. Okay, so let me draw the picture of the blow-up. So here you have E. So we take a line contained in E. And for the other, so I don't know why I took this, but you can take, so let me do as I did in my notes. It's probably not the most reasonable. No, let me take another one. Let's take L prime to be a line disjoint from L. Okay. So here I blew up a point 0, O, and I take L prime will just be the inverse image of a line not passing through O. Okay. Okay, so certainly these two lines are effective. Okay, and okay, is this, maybe this is not such a good idea. No, sorry, there was a good reason why I wanted to do that. I want to take a line which is like this, okay, which meets E in one point. So in other words, instead of taking this line here, I take a line, I take the strict transform of a line passing through O. Okay? So the intersection numbers we've already calculated, okay? So there's a duality between this space and that space, and it's given by, so EL we computed was -1. EL prime is 1 because they meet transversely at one point. And now epsilon upper star of HL is 0 because I can always choose a hyperplane which does not pass through 0, so it will not meet L, and epsilon upper star of L prime is 1. Okay, so this defines the duality completely here. And so actually, so the line L is contracted by a point, it's contracted by epsilon to a point, and the line L prime is also contracted by this second morphism. Okay? And so this is one of the interesting points about this whole theory of cones is that whenever, so I'll let you, maybe I'll explain that because it's an important point. So fundamental remark, if you have a variety X and a morphism, usually my morphism were called pi, I think. Pi from X to Y, which contracts a curve, so assume you have a curve here such that pi of C is a point, then the ray that it spans in that space over there is extremal. Okay, and this is very simple. Okay, so here I'm assuming that everything is projective. This is really important. Okay, so basically, so extremal in the Morricone, of course. So basically, assume that you can split C as the sum of two classes like this. Okay, so here there are elements of the Morricone. No, this is not true in this generality. Sorry, yeah. I got carried away here. No, this is not true. This is not extremal in general, so sorry. Forget about this. Yeah, but it's a bit... it's a bit too complicated. Anyway, so forget about this. But I mean, it's not entirely stupid, but it is not as written as it is false. But it is true in that case. Okay, let's put it this way. And so, in particular, so since L is contracted by this morphism and L prime is contracted with that morphism, and these two classes are different, and we know that the cone in a two-dimensional space looks like a slice of pizza, it has to be this. Okay, so it's a very simple cone, as all cones in the plane. Let us look at the how this thing here fits in with Maury's theorem. So either you already know that X is a Fano variety, okay? And if you don't know it, we make the computation. So actually, it's the canonical class of a blow-up. It's very easy to compute. It's first of all the inverse image of the canonical class of the base, which is here minus S plus n plus 1 H plus n minus 1 E. Okay? So since we have all the intersection numbers, we see that Kx L, for example, is equal to what? So the intersection number here is 0, so it doesn't count, and here it's minus n minus 1. And the intersection number of Kx with L prime is minus n plus 1 plus n minus 1, so it's minus 2. Okay, so they are both, these rays are what we call Kx negative, meaning that the intersection with Kx is negative. Okay. So the whole cone actually fits into, there is no part here. Okay, this is 0. And so we are all in the good part of the cone. Notice, so this we forget. Maybe I should erase it since it's false. So in particular, this computation does show that X is a Fano variety, because according to Kleinman's criterion, Kx is, so the Kx orthogonal is somewhere in here. Okay, and Kx is positive on the entire Maury cone. Minus Kx is positive because Kx is negative. Okay, so by Kleinman's criterion, minus Kx is ample. So in other words, X is a Fano variety. I should also make a general remark here, is that when X is Fano in general, this part here is 0. Okay, because we know that Kx is negative on that cone here. So and since I said, I didn't write, but I said that these extremal rays can only accumulate on the orthogonal of Kx, and the orthogonal of Kx is far away, okay? Picture looks like this, okay? So they cannot accumulate here. So it means that they don't accumulate, which means that there are finitely many of them. The set I here is finite, and in this case, the Maury cone is polyhedral. So a cone is polyhedral if it is the cone generated by a finite set. So, okay, so okay, so of course I don't have time to prove Maury's theorem. The proof is in the notes. I mean, it's not that complicated. So I'm a bit lost in my okay, there's I want So let me erase this example. Let me erase here. You never know. There's a proposition which is very important. So, X smooth projective, as usual, and assume that R is a Kx negative extremal ray. Like these two guys here. Okay? Then there exists an F divisor MR on X such that R is the trace of the, so it's a set of points in the Morricone such that MRZ is 0. Okay, moreover, MMR minus Kx is ample for all M sufficiently large. Okay, so what does it mean? So we say that MR is a supporting divisor of the ray. Okay, so in the case of a plane cone like this, there's only one possibility. Okay, so this is the extremal ray, and the supporting divisor has to be this one. I mean the orthogonal. Okay, there is no choice. But if you think about a higher dimensional cone, so assume that your ray is here, then a supporting divisor is any plane, corresponds to any plane which touches the cone only along that ray. Okay, so here you have a whole range of possibilities. So let me sketch the proof maybe. So there's something that comes out of the proof of this theorem here. So first of all, R is a Kx negative extremal ray, so it is one of these. Okay? Because I said that these rays here were all the Kx negative extremal rays. Okay? So R is spanned by the class of rational curve gamma. Okay? And so there's something that comes out of the proof of this theorem here is that if you look at the smaller cone, which is the same as this guy, but you just leave out okay, so I'm taking the same sum except that I leave out this guy here. So in other words, so this is my ray here, and I leave it out. So the cone, the new cone will be here. Okay. So the fact that comes out of the proof is that this is closed. It's a closed cone, strictly contained in the Morricone. Okay? let me. So another thing that comes out of Morris' theorem is that there's a rational structure on this vector space where everything is taking place. Remember, we obtain this n1 x as the tensor product with R. Okay, so this is same as we obtained the space of divisors by taking tensor product with R. The same is true for the space of one cycles. So there is an integral structure, meaning that the curves have integral coefficients for this, or let's say rational coefficients for this structure. So in particular, since R contains a rational point here, it's not difficult to see that you can choose R to be an integer, meaning a divisor. Okay. Sorry, I'm going too fast. Okay, sorry. Just forget what I said. Okay. So this comes from the theory of closed cones, of convex cones. There exists a supporting hyperplane H of R, which is a positive on C. Okay, so let me explain, maybe this is not very clear. So the picture is here, okay? So from the theory of convex cones, there always exists a supporting hyperplane, meaning a hyperplane which touches the cone only along that ray, okay? And this, what I'm saying here is that you can also choose this hyperplane so that it is strictly positive on this smaller cone. Okay? So what I mean here is that for all z in the Morris cone, hz equals 0 implies z belongs to R. So this is the meaning of a hyperplane. And also for all z in C non-zero, minus 0, hz is positive. Okay. So it seems true on the picture here, right? You have an extremal ray, you have a smaller cone, and so you can find a hyperplane which touches this cone here only along R and which doesn't touch at all C except at the vertex. Okay, so what I was saying, I was ahead of myself. What I was saying is that this thing here comes from H is a priori a real hyperplane. And so what I was saying here is that you can, since R is itself spanned by a rational point, you can move H a little bit around so that H is rational, meaning that it's orthogonal, which is a line in the dual space. This line is spanned by the class of a true divisor. By a divisor, the class of a divisor, which I call MR. Okay, so maybe I can erase this. So now we want to prove this statement here. So how do we prove that something is ample? Well, we have to prove that it's positive on the Morris cone. Okay, this is Kleiman's criterion. So how do we prove that this is positive? How do we prove that for when Z is in the Murray cone? Well, so remember, by the definition here of C, we can always write Z as a point, let's say C, which is in the smaller cone, plus some multiple of, I never gave a, well, let's use this. Okay, so what do we know? We know that MR, this is non-negative. Okay, so when Z is in the Murray cone. So this is non-negative. Okay, so now let me put it this way. We know that MR is positive on this smaller cone. Okay, this is the this property here. We know that on the ray, MR is 0 and minus kx is positive. Okay, so this is sort of, so lambda is non-negative. So here MR is 0 and minus kx is positive. And in here, MR is strictly positive and minus kx we don't know. Okay? So it's not difficult to see. It's just a reasoning about geometry in a Euclidean space that when M is sufficiently large, then the whole thing will be positive on any element like this. Okay? So we get this. Okay? On this part, there's never a problem. Okay? It's always positive because MR is 0 and this guy is positive. Here there might be a problem, but we know that this guy is positive. So you just take M large enough so that it overcomes the possible bad behavior here. So you have to do you have to be a little bit careful, but that's basically the idea. So once we have this, this proves that this is ample. Okay, so where do we go next? The next step is what is called a contraction of extremal rays. So remember, in the very naive example here, we're very happy because so we had two extremal rays, and for each one there was a morphism which contracted these rays. And so the general question is, can one contract extremal rays? Okay, so this is not always possible, but it turns out to be possible for kx negative extremal rays. Okay. So what do I mean by contraction? Okay, a contraction of a ray, this you can take that as a definition. Of a ray R is a morphism CR from X surjective morphism from X to Y, Y projective, normal. So actually, we want to be not only a morphism, but what is called a fibration, so something with connected fibers. Such that for any curve in X, C is contracted, meaning that CR of C is a point, if and only if the class of C belongs to R. So when I mean ray, I mean extremal ray. it has to be extremal. This is what I was trying to say earlier. But if you have this property, then R is extremal.
Why do you say vibration?
Because you want a fibration. I mean, once you have a morphism, then you can have a fibration by a Stein factorization. But so this is not really important.
It's not true. You need some assumption.
Sorry?
You need some assumption. Otherwise, it's not true that
It's a definition.
No, I mean, what you just say, that extremal rate means that, I mean, it must be an extremal rate.
With this here,
Well, assume that you contact P1 plus P1. It's not an extremal rate. I mean, you're not assuming Y smooth. Right?
I'm not assuming Y is smooth, no.
So take something contract P1 plus P1. Any curve is not, an extremal rate. I mean, the diagonal.
But it's not contracted.
I mean, suppose that P1 plus P1 is contracted to a point.
Yes?
The diagonal is not going to be extremal rate, right? You need something like K number of x equal to K number 1, y minus 1, something, or plus 1, something like that.
Okay, we can discuss that later. It's not important for here. No, I mean, I'm assuming that R is extremal, so. What would be a candidate for something for a contraction?
The more general situation gonna be contraction of the face.
Yeah, this is what I was trying to say earlier. Yeah. I'm not sure I agree with him, but we'll see. Okay, what would be a candidate for a contraction here? So you see that by definition, so X is supposed to be projective. So if I take an ample divisor on Y and I pull it back to X, it will be a Neff divisor. I forgot to say something. Ah, yeah, it is. So if I take an ample divisor on Y, I pull it back to X, this will be Neff, because it's the pullback of a Neff divisor, of an ample divisor. And also, its intersection with R will be 0. Okay, because so what I mean here is that anytime you have a class in here, for example, a contracted curve in here, then since it is contracted, it's this intersection product is 0. Okay. So if you look at the proposition here, you see that a candidate for a divisor which defines this contraction would be MR, or any multiple of MR. Okay. So it would be nice. Let's say assume that MR is base point free for M sufficiently large. Okay, so base point free means that it defines a morphism from X to some projective space, and I call Y the normalization of the image, or let's say the Stein factorization of the morphism, but this is not important. Okay, so now if you look at this situation, this map here will be a contraction, and this is okay. So certainly it contracts any curve C with class in R, because it has degree 0 on that curve, and it contracts only those curves. The problem is this. Okay, this is not obvious. Why should it be a base point free? And it is actually the case, but so I think this is known only in characteristic 0. And this is a consequence of Kawamata's base point free theorem. And it uses this thing here, which we haven't used. So base point free theorem so this is Kawamata. So it says that if you have D, an F divisor, such that AD minus KX is ample, or let's say F and big actually, is F and big. But in our case it is ample for some positive A, then, so, sorry, maybe I never used this base point free. This is the same as globally generated, okay? It means that it defines a morphism. Then MD is globally generated base point free for M large enough, and this is in characteristic 0. I mean, basically over C. So this theorem applies exactly to our situation because of this hypothesis, I mean, this property here of MR, and it says that some multiple of MR defines a contraction. Okay? So, of course, I don't have time now. Let me take just 3 minutes. What comes next? So I won't have time to explain. So either Paolo will do it, or you can read my notes over the weekend, which probably the second solution is better. So for reasons that I explained in the notes that I won't have time to go into here, it's given a variety smooth projective variety, we would like to have a model a model, which means some birational model. So let's something like this with kx prime nef. So this is not always possible. I mean, if you look closely at what I've done during this series of lectures, you can see that when x is uniral, this is not possible. I mean, basically because if you have a uniral variety in characteristic 0, it's covered by free rational curves, and kx cannot, it's never nef on a free rational curve, okay? So this is not possible. So we have to make some additional assumptions. But anyway, so even if we forget about this case, how do you get to something nef? Well, Maury's idea is that you start from your variety x, and you want to sort of kill the curves where kx has negative degrees. Okay? And so where kx is negative, by contracting them. As we did. Okay. So, in other words, you start from x, you pick a kx negative extreme array, and you contract it. Okay. So there are three cases which are very different. The first case is when the dimension of y is smaller than the dimension of x. So we said that the contraction is of fiber type. And in that case, it's not very difficult to see that x is actually unirolled. Okay, so this is the case which sort of prevents you from having a minimal model in that case. The second case, I mean, there are three cases, and in both cases 2 and 3, x and y have the same dimension, so CR is birational because its fibers are connected. But you have two cases. Either the exceptional locus of CR is a divisor, so the exceptional locus of, say, a birational morphism is the set of points where the morphism is not a local isomorphism. Okay? So for a blow-up, for example, it's the exceptional divisor. Or it's not a divisor, meaning that its codimension is at least 2. So in that case, it's not too bad in the sense that the y here might be singular, but still locally factorial. So locally factorial means that any Veil divisor has a multiple which is Cartier. So in that sense, it's okay because you can still do intersection theory between divisors and curves. Okay. The bad news is that Morris theorem, as I stated it, is only true for smooth varieties. So there's already a problem here. In that case here, the y is very bad. Okay, it has very bad singularity. It's not, never, it's not locally Q factorial. Meaning that there are always Veil divisors for which no multiple is Cartier. Okay? And in that case, you really cannot do anything. I mean, you cannot intersect these divisors with curves. Okay? So this is bad. So the solution here, and I'm sure that Paolo will talk more about this, is, and Radu already mentioned that, is that you want to do a flip. So a flip consists as into changing x into some other guy here. So this will be a birational morphism. X plus will have singularities not too bad, like this. And so what we gain in here is that, so by definition, kx has negative degree on curves contracted by the contraction. It's part of the whole story. But so the point of the flip is that kx plus now has positive degrees on the curves contracted by y. So we've sort of a situation is a little bit better. We killed kx negative curves in some sense. Okay. So then you want to repeat the process. So already we saw that you need to allow singularities. And the problem is that you want the process to terminate also. So in these cases, it's okay because the Picard number of x decreases by 1. Okay? In this case, the bad news is that the Picard number of x is the same as the Picard number of x plus. So you might be flipping for the rest of your life forever, okay? Which you don't want to do, right? So I guess I'll stop here. I'm already 10 minutes over time. And so I'm sorry, Paolo, I didn't spend... It's up to you now. Thank you.